Today we're going to be covering IP SLA and enhanced object tracking. Might take an hour and a half, maybe a little bit less than that. It's not a really complicated section. And then we're going to be wrapping up today by doing a separate lesson on GRE and IP tunneling. So how does the audio sound, guys? Sound pretty good? It's good now? Yeah. When I was starting the recording, it kind of phased out a little bit. Just let me know. I'll keep monitoring. And I'm actually not on my phone this time. I think on the weekend, on a Sunday, people are using the bandwidth a little bit less here at the hotel, so the audio is a little bit better. So anyway, we're going to go ahead and get started. We'll be using this topology again, doing our path control. We actually have a different topology. I put it in the Google Drive for the discussion on GRE tunneling. So we'll load that topology when we get into that discussion. So IP SLA and object tracking, what we're going to talk about in this section here is how we get application level visibility to our lower layer control features. We can always get network visibility through mechanisms in our routing protocols like neighbor relationships and adjacency information, or we can get information about our protocols other ways through layer 2 link mechanisms or even physical layer heartbeat mechanisms. But what if we want to get some sort of visibility at the application layer? Now, IP SLA can, just like policy-based routing, can be a really, really complex discussion. There are so many different types of probes that you can establish, and whether you're going to use a self-contained probe or you're going to have an IP SLA responder. So I'm going to talk about the theory of this primarily for the purposes of the written exam, but we're going to get into some of the practical applications as we kind of move through the discussion here. So why do we need application tracking? We'll talk a little bit about that. What is IP service level agreement? What is enhanced object tracking, or what you might see referred to as EOT? And how can we incorporate this? We kind of saw towards the end of our last lesson, this incorporated into our policy-based routing so that we can get reliable policy-based routing rules, right? So we'll talk about why is application tracking needed and so on. Actually, when we talk about general routing principles, right, the whole concept of routing, switching, and then finally encapsulation, what is the primary concern about the routing, right? What is the criteria that the router uses to install a route, right? We do that route recursion that we talked about, and we try to recurse a destination based on the next hop address. Once we do our route recursion, we're then going to identify the outgoing interface for the traffic as well. The result is going to be that the route state shares its fate with the link up-down state of the interface that's tied to the particular route itself. Just something to keep in mind. Well, what happens if the link up-down state doesn't change or the link state doesn't change? What really happens? All right. Now, the real question is, what is that criteria that's required for the up-down state, right? What is that criteria? A link up means that there's local keep alives. If it's not a point-to-point link, there's some sort of local keep alive that's happening between the local switch or maybe the local frame relay provider or the local PE router that provides that link status. So the router needs to recurse to the next hop, which then gets tied to the local exit interface. The route is going to get withdrawn if local reachability is removed. But oftentimes, if you have an example of something like this, where I have, let me pull up my paint here. Where I have a topology, oftentimes the WAN connections are going to be, they're not going to be direct point-to-point links, right? So I might have, for example, a router here and that router might be connected to some service provider cloud, and I have a router at the other side of that network. Well, guess what? That router at the other side of the network is also connected to that cloud. So the link state is going to be based on this connection locally between the provider edge router and the customer edge router. So even if this router goes down, this link state is still up. That's going to pose a problem because the route is not going to get withdrawn in this case because local reachability is not being removed from the process. We will discuss other solutions to this later on. Of course, you could always rely on network layer reachability between peering relationships, like if these two routers were EIGRP peers or something like that. But we'll also talk about a layer 2 keep alive mechanism, potentially to find out if there's any failures in the transit path between endpoints. Or we can talk about bidirectional forwarding detection, which we can use with our routing protocols to identify if there are any issues between those different networks. All right. Just because we have local link connectivity does not mean we have end-to-end reachability, and that's really the challenge that we have to deal with. It's going to totally depend on the encapsulation. What's the underlying layer 1 design? All right. In fact, if I go into a router here, if we look at our topology, we've got this WAN cloud in between, or even BR2 here in this case. If I go into BR1 and I do a show IP interface brief, maybe it's thinking. There we go. Show IP interface brief. Come on now. Show IP interface brief. So when we run our show IP interface brief, we can see from this particular output, here that we have, as an example, the status column. So this status column is going to indicate essentially the layer 1 status of our communication process. So if I see an up here in this particular case, that means that the physical layer is up. Now, if I were to go into this diagram here and change, let me turn off my pen here. Let's turn that off. And I was going to my diagram here, and I was to bring down this serial link between HQ and BR2. It wouldn't have any effect on the overall function of BR1 and the link status of BR1. All right. IP SLA and object tracking is what we can use to mitigate this particular problem. Dynamic routing could solve the problem, but static routing, policy-based routing, it's not going to give us the ability to effectively identify a solution in this particular case. So we oftentimes will have to incorporate IP SLA in the process. All right. So what is IP SLA and why would I use it? Well, let's go ahead and talk a little bit about some of the basic concepts. IP SLAs, which stands for Service Level Agreements, is going to give you the ability to analyze different IP service levels for IP applications and services. That could be at the network layer, it could be at the transport layer, and there's even there are some elements that allow us to identify the services at the at the application layer as well. The idea is that we're providing some sort of active traffic monitoring scenario where we generate traffic and measure network performance based on those characteristics. So if we're using IP SLAs, we can measure and maybe provide some sort of service level agreement. We can do an overall network assessment, quality of service. We have ease of deployment, of course, in this case, and so on. Are we having... So, you know, there's a bunch of different things that we can monitor as part of this process. And we're going to take a look at some of the configurations. We're not going to go through every aspect because, again, there are, you know, 30 or 40 different types of probes depending on the platform and the iOS that you're running that you can set up for the monitoring, right? But before we get into the specifics here, I just want to give you guys a little bit of background information on the IP SLA technology. We'll fill in some of the notes in our notepad as well, based on some of the things that that I think are important for you to know, not only for the lab but for the written exam. So we'll start with IP SLA, and we can use IP SLA for monitoring all kinds of things. And what you're monitoring will depend on whether or not you need an IP SLA collector or an IP SLA responder in the network. We'll talk a little bit about the difference between an IP SLA collector and a responder. But we can monitor, well, first of all, we know it simulates network traffic. All right. When I say simulates, I mean it's actually generating network traffic, but it's simulating hopefully what we're trying to monitor as far as the function, right? So we can collect information about reachability. We can collect information about response times. We could measure one-way latency When I say response times, I'm talking about like maybe a TCP session, like an HTTP session request, or a DHCP discover request or something like that. We can monitor jitter, which is that inter-packet delay variance that comes between the packets. We could monitor packet loss, perhaps, maybe even voice quality scoring, which would include something like a mean opinion score for voice traffic. We can measure all kinds of things, server response time, etc. I'm just going to put in etc. here because there's, like I said, there's a bunch of stuff that we can monitor within IP SLA. All right. Now, IP SLA does perform active monitoring. It essentially generates real traffic, and then we analyze that real traffic to measure the performance either from different Cisco iOS devices in the network or to a remote device like an application server or something like that. Measurement statistics that we collect will depend on what the IP SLA operation is that we're running, but we can definitely use that information for doing problem analysis, or we can use it for dynamic policy, right? Identifying whether a policy-based routing policy should be enacted or whether or not a static route should be used or not used, and so on. And we'll take a look at how we kind of incorporate all of those elements in our configuration. All right. Depending on whatever specific IP SLA operation you decide to run, statistics of maybe delay or packet loss, jitter, maybe looking at packet sequencing, server response times, etc., will depend on how you configure the IP SLA probes, but what you have available to you, and we'll see this in our configuration, will also depend on the CLI for the particular platform, right? So this is just like policy-based routing is going to be something that's kind of more platform specific or iOS specific as to what you can configure. Now for the CCIE lab, you're only going to have to be familiar with some basic IP SLA concepts. For the written exam, maybe a little bit more, but I'm going to demonstrate some of the most basic IP SLA concepts in our topology to see if we can't identify how we can create these enhanced object tracking elements, creating these tracking objects, and then tie those into an IP SLA configuration. All right. Some of the packets do have configurable values, so we could maybe specify a source or destination IP address, We can even specify what specific UDP or TCP port numbers we would use. We can also put in a toss byte value like DSCP or prefix bits if we want to add prefix bits. We can specify a website address, all kinds of things. Now IP SLA is completely layer 2 transport independent. Let me put that in here. Completely layer 2 transport independent. All right, so we can configure these over any network based on what we want to measure. So what are some of the IP SLA operations that I listed? Well, I'm just going to list a few of them here. So we've got the ability to do delay, and here we can measure either one way or round trip in this case. That will most likely require the use of some sort of IP SLA responder, something that's going to respond to the IP SLA. We can measure jitter, which is usually in per direction, right? Jitter is always a value that we would typically measure per direction. We can match against packet loss. So I could say packet loss as well. That's going to be directional as well. We can match against packet ordering, what we call packet sequencing or packet order. Probably beyond the scope of what we're doing in this class, but and again, I'm not going to demonstrate all of these. We can even match against the path that's taken. That's going to be based on the hops in the network. We can measure connectivity, like link state, link up down state, and that's going to be directional based on how the traffic is flowing. We can measure on server or application load times. So I do an HTTPS or HTTP request, how long does it take? And like I said, voice quality scores like mean opinion scores, which are, it's a tool that we typically use to measure the quality of voice that's been digitized to be packetized and sent over the network. So lots and lots of options here with regard to what we can measure. We can also even use things like Cisco Prime and other elements to be able to control these different configurations. All right. Let me see here. So when we're measuring specific pieces, depending on what we decide to measure, there are essentially a couple of different measurements that can take place. We can do end-to-end measurements, which means that we're measuring the performance from one end of the network all the way to the other end of the network, or wherever it is that we're trying to go. We can measure things like I said, delay, jitter, packet loss, layer 3 connectivity, and so on. And a lot of these probes are really easy to implement, but depending on what it is that you're trying to accomplish will define how complex the deployment option is going to be. All right. IP SLA monitoring can give us obviously the ability to monitor and measure and verify, agreements that we might have with a particular service provider. We can do network health assessments and so on. But for the most part, and most likely what you're going to have to know for the exam is you're going to have to know, essentially know reachability monitoring, right? How am I going to incorporate the use of IP SLA to be able to monitor reachability to a particular destination? All right. Now, there are some pieces that I'll talk about when we go through the configuration. It depends on, like I said, what we're trying to measure. We're not going to obviously set up a IP SLA collector or responder in this particular case, but there are physical iOS devices that you could deploy that provide those physical probe functionality. Okay, that's going to be beyond the scope of generally what the requirements are for the lab itself. You're not going to have to go in and set up a IP SLA responder specifically to respond to particular IP SLA configuration. There are some basic tasks that we're going to take a look at. As far as configuration goes, it's a pretty straightforward process. Configuration includes, one, you're going to enable the IP SLA responder if you need one. I'll talk about what a responder is a little bit later on. Not always needed. It depends on the probe that you set up. So probes that are going to measure things like jitter and delays, typically in those cases, you're going to need some sort of responder to be able to measure those timestamps, right? To be able to measure those time values. So not something that we typically will worry about too much. Like I said, definitely not on the test. You're not going to have to worry about that. All right. The next thing is to set up the IP SLA operation. So configure your IP SLA operation. That might be like a ICMP echo or some other type of probe where you're just performing some action. Then we're going to configure the options for that specific probe, or what we call an IP SLA operation. And again, depending on what type of operation it is that you're configuring, will determine, what type of pieces or elements you can configure with that particular probe. We're going to configure our threshold conditions. And then we will go in and schedule the operation. So schedule the IP SLA probe operation to run. We'll talk more about that when we get that. We can make it run for a specific period of time. We can have it start at a specific time. We can have it start and then run indefinitely. Just depends what our overall objective is, and then finally verify the results of that particular operation. And typically that's going to be a concept where we're trying to monitor, is the probe up or is the probe down? Are we seeing events occurring or not occurring or whatever, based on whatever our configuration is. So those are the basic steps, and we're going to take a look at that a little bit later on as part of our configuration. Now, I've mentioned an IP SLA responder a few times, and there's also an SLA control protocol. You probably won't need to know much about the IP SLA responder for the written or for the lab exam. You'll probably need to know a little bit about it for the written exam, and you might need to know a little bit about the control protocol for the written exam. But you don't really need to know too much of this. I'm not going to get into this in too much detail. But basically, what an IP SLA responder is a SLA component that's actually embedded in a destination router, a Cisco device, that basically allows that particular device to anticipate the messages it's getting from the probe and then respond to the IP SLA request packets. So it's an active device in the network, specifically programmed to respond, interpret and respond to specific probes. All right. And again, the responder provides a little bit more visibility because we can do accurate measurements without any kind of dedicated probes. We don't have to have like a a physically dedicated piece of hardware that's going to do this. There's a control protocol that's actually used in this process that's used by the responder specifically to respond to specific probe requests. If we're doing specific network performance measurements, that's typically when you're going to need an IP SLA responder because we're actually measuring things in real time like packet loss, delay, jitter, and so on. All right. When you actually set up the IP SLA responder, once we get the control messages, the responder can then enable specific UDP or TCP ports for the duration of that particular process. So we're going to accept requests, we're going to respond to them, and then that'll give us that visibility. Okay. Now I don't know that we necessarily need to get into the specifics of how response times are calculated and time stamping and all that. I would suggest that you guys, if you're really interested in learning about all of that part of it, or the specifics of the responder, where we're talking about things like the TS3 or TS4 timers, TS2 timers. That TS stands for timestamp. There's a timer on the source router called the T1 timer. That's the exit timer on the source router. And then we have a T2 timer, which is the time that comes in on the target router. And then we have a responder time, T3, and then we have finally T4, which is the time that arrives at the source router. But again, I don't think it's really necessary that you understand those specific pieces. But we'll get into that a little bit. We actually won't probably talk about that too much in the rest of this class. But again, go take a look at some of that documentation online, and you can see all about the timer operations. For the most part, what we're going to be concerned about with regard to IP SLA is to allow us to identify whether or not the application level checks can be utilized, right? To be able to test for reachability and so on. Again, the types of checks that you can perform are somewhat varied between different platforms and different operating systems. It will depend on the operating system version. You could do an ICMP echo request, which is one of the more common ones. You can do a UDP ping if you want to do some sort of upper layer check with an ICMP message. We could do something like a TCP connect to test a TCP connection. We can do a DNS query to a DNS server, not necessarily to test the DNS application, but maybe to test the response time, what we call the latency response of the application itself. I could do a DHCP request, again, to a DHCP server to check the latency response. I'm not going to demonstrate all of these concepts. Again, just like policy-based routing, it can get rather complex. Now, another piece to this is, which I think is really important, is the enhanced object tracking. Let me put this in bold here because that's going to be really kind of another piece, what we call EOT, which is kind of the glue between IP SLA and whatever feature we're trying to apply this to. So it could be a route map, it could be a redistribution process, it could be a static route, it could be applying administrative distance values to dynamic routing or whatever, all right? When we create an object, it's going to track the IP SLA instance, and then that tracking object is then going to have a status based on the status of the probe itself, all right? What kind of things can we track? We can use this for HSRP or GLBP or VRRP to change priority levels and whatnot in those first hop redundancy protocols. We can use it to tie it into a static route. I'll show you guys how that works a little bit later on. We already saw in the last example, or the last lesson, remember how we had the policy-based routing where we said next hop or set the next hop to a specific IP address, but we're going to go ahead and verify availability based on a tracking object. The results of the application layer test would apply to whatever feature that particular application is using. So, for example, if I have a IP SLA probe that is performing a simple ICMP echo request test, basically we call this just a reachability test, I would then set up a tracking object, object based on that probe, and then then based on that, I would apply the tracking object to an application, like static routing or policy-based routing. This may be a little bit confusing right now. As with anything that we talk about with route manipulation and just managing flows in a device, taking a look at the configuration is going to be a lot more useful for us, and it will give us more, kind of more of an understanding of how everything works. All right. All right. So, what are some of the IP SLA operation types? Like I said, ICMP echo, that's pretty common. ICMP jitter, HTTP get, right? This is a really common probe actually, because I can ping my web server, but it doesn't mean that I can actually get application layer data. So just because I can ping a web server doesn't mean I can get application layer data. That means that the application is probably not functioning. So I can use an HTTP get. I can do an FTP get or put. DNS queries like we talked about. ICMP path echoes, path jitter, UDP echo, UDP jitter, all different kinds of things. I've mentioned them a few times already. All right. In any event, whatever the probe is, the ultimate goal is to look at the application and make a decision rather than looking at layer 1 or layer 2. We're trying to do things at the application layer. And there are a lot of IP SLAs that are just simply based on connectivity tests. Usually the IP SLAs that are based solely on connectivity tests are not going to have anything to do with an IP SLA responder. If you're going to have anything that's going to require a specific response, like jitter or round trip time and stuff like that, then you're going to need an IP SLA responder. All right, I've mentioned that a few times as well already. All right, so if I came into this device here and I did a show IP interface brief pipe exclude unassigned, I can see that I have 4 active interfaces on this particular router. Now, some of these interfaces are tied, at least one of the interfaces is tied to physical layer. This serial 2.2 interface, for example, is tied to the physical layer status. So if this router on the other side goes down, no problem. This router BR1 is going to know that that goes down. So I mentioned this already, but the top 2 links, the BR2 link and the WAN link, does not rely on physical link status to identify whether the interface is going to be up or down. All right. If I was to create a route map that points to a down interface, that the PBR routing is going to break because the policy, well, it depends, right? I think I demonstrated this in the last lesson as well. So if I had some sort of policy, let me see if I can do this real quick. So let me go into BR2 and do a quick show route map. see if I have any route maps. So let's say that I am trying to control traffic flow from this PC on the right over to this 100.1 loopback on the left. As you guys saw before, I want to go ahead and create an IP access list extended, and we'll just call it PBR. We're going to say permit IP from host, and let me see the PC. Do show IP interface brief, pipe include up. So I've got 192.168.110.20. All right. So I'm going to go back to BR2. I'm going to say the traffic is going to be sourced from 192.168.110.20. And we'll say that it's going to go to 192.168.100.1. I believe that is the loop back on this guy here. So I'm creating an access list to match a specific set of traffic. And let's see how routing is going to take place. Do a show IP route 192.168.100.0. So right now, the traffic is going to route over 1010 40.1. So if I look at my topology, that makes sense. 101040 should be this. Oh, I'm in BR2. Let me go to BR1. Dang it. It's doing everything in the wrong router. Let's clean this up a little bit. No IP access dash list extended, PBR. Let's go to BR1. Try and do this on the right router. Config T. IP access dash list extended, PBR. And let's go to BR2 and just make this easy to copy. And show route map. Make sure I don't have any route maps. All right. So if I do a show IP route 192.168.100.0, we can see that, yeah, that makes sense. We're using the WAN link 10.10.10.1 as our destination. But let's say in this particular case, I want to go ahead and route that traffic rather than from over this 10.10.10 link. I'm going to go ahead and send it up to the serial 2.1 interface. Actually, I'll just go ahead and throw it out the serial 2.1 exit interface. So let's take a look at that configuration. All right, so route map, PBR permit 10, match IP address, PBR, set interface, serial 2/1. So I'm setting the exit interface for this traffic over serial 2.1. And then the last step would then be to go ahead and apply this policy to Ethernet 1.1. All right. Interface Ethernet 1.1, IP policy, route map PBR. Okay. So if I do a show IP policy, I can see that we have a route map applied to the interface. If I do a show route map, excuse me, do show route map, I can see that the set clause is 2.1. We don't have any actual traffic yet, so let's go ahead and do that. And I'm doing ping 192.168.100.1. The ping goes through. If I go back to BR1, I should see packets matching that particular destination. Now, if I go back to my PC and I do a trace route to 192.168.100.1, which is also an ICMP message, by the way, I can see that we're using that serial link 30.2 and then we're going over 40.1. So the policy is set up to work just fine. All right, and we did this demonstration the last time. Only this time I'm going to take my time and I'm going to show you how we can create a probe that will work with policy-based routing to make sure that PBR doesn't get broken when we have an issue. All right, so we're sending the traffic over this link here as opposed to what normal routing would do in this particular case. All right, so now if I come into my topology and I shut down serial 20 on BR2, the problem that we're going to see, let's go into interface serial 20 and do a shut. If I go back to my PC and I do my ping, that should stop working. Did I shut down the wrong interface? Do show, let's show route map. Did I shut down the wrong interface? Do show IP interface brief. No, I shut down the right interface. 40.2 is shut down. That ping should, let me try traceroute and see which way it's going. 192.168.100.1.
Route 2.0?
Sorry?
2.1?
No, I was actually trying to shut down, 20. In this case, I'm sending the traffic out of 2.1, but I wanted to shut down 2.0 over here because the status of this link should not affect the policy. As long as this interface is up, the router should be trying to send that traffic over this interface. But I see what's happening here is the traffic's going to 30.2, and then it's being rerouted back to 30.1, and then it's being sent over 10.10.10.1. So what I'm going to have to do is I'm going to have to specify a next hop instead of just specifying an exit interface, because that's essentially what's happening. The traffic is hitting the router. It's going up here to, because if I go to BR2, in any event, it's definitely not optimal anyway, right? I don't want to send the traffic up to router 2 and then back down to router 1 and then over the serial link. But if I do a quick show, I have it right here. So serial 2.1 is 32. Is that, yeah, that's the interface that I left up. Serial 2.1 is 32, so that's exactly what's happening. The traffic is going up to 30.2, then it's being sent back to router 1, and then it's being routed over the link. So regardless, I mean, it's not really the ideal thing that I wanted to show you. I was hoping that it would just time out. It might if I go ahead and change my set conditions, do show route map, config t, do show run section route map. And let's go into route map, PBR, permit 10. And instead of saying set interface, let's do a site IP next hop. In this case, we're going to do 10.10.30.2. Because what that would do at least is possibly create a loop. I'm just trying to get suboptimal processes running here. So I'm going to send it to 30.2. Do show run section route map. All right. And let's do a no set interface. All right. And do show run section route map again. All right. So now let's go and do our ping, see what we get. Still working, but it's basically doing exactly the same thing. So anyway, let's just assume that that's, all right, fine. It didn't break completely, but it's definitely not doing suboptimal routing. I don't want to send the traffic up to R2 only to have the traffic get back sent, or BR2 to have it sent back to BR1. What I'd rather have is something in the system that identifies that this link is down so that we don't use policy-based routing, we don't send the traffic in that direction in the first place. That we go ahead and either revert back to our normal routing process, or we set up a secondary policy, right? That maybe says, okay, well, if this link is down, let's go ahead and use this bottom link or whatever. What we're going to do is we're going to set it up so that we just have a process that says, you know what? If for some reason I can't get to that top path, or the top path is not responding, then I'm going to go ahead and just bypass policy-based routing altogether. All right. I'm losing the gracefulness of this discussion here, but basically you understand the concept. The link status on this interface has no bearing as to whether or not the policy, if this link went down, the policy would simply say, well, it's not a possibility because I don't have my route recursion fails, and I'm not going to be able to route to that particular destination. All right. So let's go ahead and do this, right? In a lot of cases, we're going to pretty much use an ICMP reachability probe. That's most likely what you'd have to know for the lab anyway, to do some sort of IP ICMP reachability. So let's go ahead and start to configure that on BR1. BR1, of course, is the router that's doing all of the policy routing anyway. So if I come in here and I say IP SLA, first of all, you can see there's a whole bunch of options that you can configure with IP SLA. So it can be really, really complicated. Again, kind of beyond the scope of what we're doing in this class to talk about every single option. Just like policy-based routing, you kind of want to play around with it. But we're going to go ahead and create a probe based on a number. So let's just call it 1 for BR1. And if I use the question mark here, you can see that I can set up a DHCP probe. I can set up a DNS probe. There's some Ethernet operations that I can run. Excuse me. So if I type Ethernet, for example, I can see if there's a echo based on 802.1ag, jitter operations over Ethernet, and so on. Again, really beyond the scope to really kind of talk about every single component that we can set up. I'll maybe go in a notepad and show you a couple of examples of maybe like a DNS probe or an HTTP probe. I'll just type it in the command line, in the notepad as a command line instruction. But what we're trying to figure out is what kind of trap are we going to be using in our operation? Is it an FTP trap? Is it an HTTP trap? Is it a path echo trap? And so on. I would definitely, for the written exam at very least, make sure that you're familiar with what each of these traps represent at a high level. And then, I certainly know how to configure some of the basic probes. So we're going to do an ICMP echo probe. And we're going to say, let's go ahead and ping. Now, remember, we're testing from BR1. As long as the packet can get to HQ, we feel pretty comfortable. So rather than ping the next interface, which is kind of pointless because IP SLA is going to, policy-based routing is going to already know if that interface is up or down. And rather than ping this serial interface, let's go ahead and send a ping to 2.0. And I want to source the ping from where the client's traffic is coming from, because not only am I trying to verify routing in one direction, but I'm also trying to verify routing operations in the reverse direction. If I was to ping it from, or not specify a source address, the ping would go out of whatever interface routing defines. And then in the end, what's going to end up happening is I might not be testing against the criteria that that emulate what the client's data is, if that makes sense. So we're going to do a ping over to HQ. Let's go ahead and get our IP address. Show IP interface brief, pipe include up. Oops. So we're looking at, where's my diagram? Serial 20 in this case. So if I go as serial 20, so I'm going to do a ping to that destination. All right. And I'm going to say source IP address. And let me actually do a show IP interface brief, include up. I think it's going to be the 10.10. Well, we're going to source it from the LAN side. Okay. All right. So now I've created the probe. Now what I want to do is say, okay, how many times am I going to generate the ping? So frequency, we can specify how often I'm going to create the ping. So I might say every 2 seconds. Oh, they wanted every 5 seconds there. So we'll do every 5 seconds in this case. Now, there are two other components that we can configure, which is threshold and timeout. And usually when I'm configuring IP SLA, or actually one of our customers or whoever's configuring IP SLA, they often get very confused about the difference between those two values. So what I did want to kind of talk a little bit about the difference between threshold and timeout. All right, timeout is basically the maximum amount of time that's going to be required for the SLA operation to complete. So I guess we could just say it's the timeout waiting period for the probe response. Whereas threshold is the boundary value that gets measured over the operation result. All right, let me explain what I mean by that. Maybe round trip to time if we're measuring that, jitter, whatever the value that is actually collected during the particular operation. All right, if I cross the threshold, that doesn't necessarily mean that I have some sort of SLA contract violation. These two values actually completely apply to different objects. The timeout value is going to be directly used to restart the operation. The threshold value is used to activate a response to an IP SLA violation. All right, maybe to second or trigger a secondary IP SLA operation. Since we're not using a secondary IP SLA operation, we could set the threshold to match set the threshold to match our timeout value. All right, the frequency, and this is really important. Let me actually write this down in the notepad. For IP SLA configuration, step one, we configure the probe, the trap, if you will, or what we call the probe. That's done in global configuration mode. Parentheses config pound IP SLA number. All right. Now we have frequency. We have which should always be greater than the timeout value, which should always be greater than the threshold value. All right. So how often we send the data should obviously be more often than the timeout. If I set my timeout, well, I wouldn't even let you do this, but if I set my timeout to 2 seconds and I'm only sending a ping every 5 seconds, that's not really going to make much sense, is it? All right, because I would always have a timeout situation and the probe would always be inactive. Thankfully, the iOS doesn't really let you screw that up. All right, so threshold sets the rising threshold that generates some sort of reaction to an event. It's going to store that history information as part of the IP SLA operation, and then the timeout sets the amount of time that an IP SLA operation waits for a response to the required packet. All right, I know it's confusing. Let me see if I can walk you through a scenario here. So if we configure the timeout greater than the threshold, in fact, let me give you kind of an example here. Let me type in a configuration example and see if this helps kind of make sense for you guys. All right. So let's say that I've got a IP SLA monitor. Let me do an example. IP SLA monitor 1, and we're doing some sort of echo, ICMP echo. This is not the actual syntax, I'm just kind of creating it. So we're doing some sort of echo protocol where we're pinging x.x.x.x. I'll just call it 1.1.1.1. All right, and I've set the timeout value to 500. I've set the threshold to 20, and I've set the frequency to 10. All right. So in this scenario, where did my mouse go? There it is. in this scenario, we configured the threshold greater than the timeout. So if the round trip time exceeds the timeout, but it's less than the threshold, it doesn't show the round trip time, but it will still show as a failure, if that makes sense. All right, so if I was to do a show IP SLA statistics, we'll take a look at that a little bit later on. Let's say the latest round trip time was about 35 milliseconds. That was over the threshold, but it wasn't over the timeout period. So we'll get an operational code that might indicate that we went over our threshold. Again, because we're not nesting operations with IP SLA, we don't really care about what that threshold is. But if you get into some more complex IP SLA configurations, you could trigger secondary events based on exceeding the threshold, but not exceeding the timeout. All right. I didn't explain that very well. I apologize. But in any event, these are the, this number has to be, and by the way, these are in different timer values, right? So if I say frequency is in seconds, timeout is in milliseconds. So that's why the numbers kind of look like they don't follow the rules, but timeout and threshold are in milliseconds. So in this particular case, yes, it looks like the frequency is 10, but that's 10 seconds, not 10 milliseconds. So it is, in fact, still greater than the threshold, and the threshold is, in this case, it probably wouldn't work, right? Because no, it works. Yeah, the timeout should be greater than the threshold, but it should be less than the frequency. Okay? So anyway, let's go ahead and configure it here. Let's say we've set our timeout, our frequency to 2 seconds. So let me see if it allows me to set the threshold to 2000. It did. Let me see if it allows me to set the timeout to 2000. It did. So show run pipe section IP SLA. So we've set the frequency to 5 seconds, which is greater than the timeout and the threshold, but we've made the timeout and the threshold match, which is fine because we're not trying to trigger on a secondary event. Okay? So we're going to be sending out these ICMP echo requests. Let's do a show IP SLA statistics. Do show IP SLA statistics. And we can see that the IP SLA operation ID is number 1. The number of successes is unknown. The number of failures is unknown. Okay? That's actually okay because we've missed one other part of the configuration, which is really important. But let's go ahead and update our notes here. So in our configuration, we did IP SLA 1, and we set our timeout or our frequency to 5, which is in seconds. And it looks like that was the minimum that we could set in this case. So it's, it said we could set the frequency to 1. We could, as long as the threshold is set. So let's set the threshold in this case to 1000. Let's set the timeout to 1000. And let's set the frequency to 1. All right. So 1 second is not always the greatest time when you're talking about failover, right? We typically like to deal with sub-second timers, but if we're worrying about, or if we're dealing with something on the internet or something like that, a second is usually going to be pretty easy to deal with. All right. So go ahead. Question?
No, I just lost my audio there for about 30 seconds.
Oh, okay. Yeah, it seems to be doing pretty good today, but it'll definitely be on the recording as well. Basically, I was just saying that we had set the frequency in our case to 5 because we had our threshold set at 2000. So let's go ahead and set our threshold to 1000. That's in milliseconds. And hey, Ken, can you mute your microphone there? And let's go ahead and set our timeout to 1,000 milliseconds. Again, as far as what's going to be required on the exam, you might see some scenarios on the written exam where thresholds are going to be used to trigger other events, but on the lab, you're not going to be too concerned about whether or not you've got thresholds that have to be configured. All right. All right. It's going to be a basic ICMP echo probe, and we will monitor it based on that. All right. Now, we just did our show IP SLA statistics. Step 3, verify the IP SLA configuration. And we do that with show IP SLA statistics. That's one of the statistics. That's one of the options that we have. But we missed something in the middle here, because when I do a show IP SLA statistics, I'm seeing really nothing happening here, right? We see that the IP SLA probe is configured, but the number of successes, number of failures is unknown. And that's because we haven't scheduled the probe to run. We have to schedule the probe to run in order for it to be functional. All right? There are other things that you can do within the probe itself. We can tag a route. We can set toss values. So for example, I can set the toss value of the ICMP packets. Why would I want to set the toss value? Well, maybe the packets are going to be treated differently based on the fact that they have a different priority, right? Maybe a DSCP EF packet is going to be treated differently across the network versus a DSCP best effort or DSCP 0 packet. All right. We can set the tag. There's some other values that we can set. Hold on one second. So you can set different things in your in the probe itself, because the traffic might be treated differently if you set the traffic with different values. We can't really set a whole lot of stuff here. But, specifying the VRF, where the traffic's going to be forwarded, specifying the route tag if we're testing based on a tag, specifying the type of service, and so on. All right, we're not going to set the type of service in this probe because we're not running any QoS in here anyway. And we've already seen the IP SLA configuration. It's pretty straightforward. So now what we need to do is we need to be able to activate this probe. All right. So if I do an IP SLA schedule, let me get out of the probe configuration, IP SLA schedule, and then I'm going to specify the probe that I want to schedule, and we can see that we have different options for activating the probe. I'm going to identify the lifetime of the probe, the start time of the probe, if I want the probe to run every 3 days or every 5 days or whatever. Typically, we're just going to do a start time of now. Excuse me. And then we are going to specify the lifetime as forever. All right. Oops. What did I just do there? There we go. So, and I can specify an age out time. If, for example, the probe doesn't respond for a certain period of time, and I can also specify a recurring time frame. So let's go ahead and return. Oh, it must have already taken it from before. Do a show IP SLA statistics. Yep, it was already activated from before. So we can see that the probe was sent. Now we are getting failures here. That's interesting. I thought I brought that interface up, but it's possible so that I didn't. So the return code is timeout. We might get a return code of unreachable or whatever. Those are going to be the ICMP return codes. Let me go to BR2 and do a show IP interface brief. And yep, the interface is still shut down. So it makes sense. The probe is not going to respond. So the current, the probe is seeing a bunch of different failures. All right. So let me add this to my notes. We now need to activate the probe based on a schedule. And in our case, we said in global config mode, we said IP SLA, excuse me. Well, I'll just copy it. It'll be easier that way anyway. I won't make any mistakes typing this in. So let me go up to my command here. IP SLA schedule 1, start time now, lifetime forever. All right. Pretty straightforward. I'm sure you guys have done this before too in your configurations at some point or another. All right. So now we've got the probe, but the problem is the probe is active. We're looking for that return code of success. Did I bring up that interface? Let me go interface serial 20, no shut. And I should see pretty quickly that we get some positive response times. Once the link status comes up, we're pinging every 1 second, so we should eventually get, there we go. So now we're getting success, and the return code for the IP SLA probe is okay. Basically, it means that the probe is active and up and operational. Okay? So it doesn't really matter what we're probing on. We're looking for that value right there. It could be, because we specify thresholds and variables that allow us to identify what's going to be okay and what's not going to be okay. And then based on that, we'll get a response code for a particular probe. So we're looking specifically, in this case, for a response code of okay. Now we need to tie this to some sort of application. I want to go ahead and tie this to our policy-based routing policy because that's what we created originally on BR1. If I do a quick show route map, we can see that we have our route map configured. So I'm going to go into route map, PBR, permit 10, and I'm going to do a no IP next hop, 10.10.30.2, no set IP next hop, sorry about that. And there's a dash as well, user tab completion. All right, we're going to do a set IP next hop, and we have an option here to verify the availability. So I'm going to verify the availability, not necessarily of the next hop, but I'm going to tie this into a tracking object. All right, now I kind of skipped a step here, but I'll go back and do that in a little bit. So I can say, okay, 10.10.30.2, and I want to do a 1, which is my sequence, and I'm going to do a track 1. Okay, now if I do a show track, because we reference track 1, we can see we don't actually have a tracking object set up. So I'm referencing a tracking object that's not configured. Let's see what the effect of that is on our routing here. All right, so because the tracking object is referenced and I don't have the tracking object created, the EOT, policy-based routing is failing, and it's saying, you know what, I'm going to go ahead and route based on my normal routing table. So the next step in this process is now we need to create a generic tracking object to reference the probe. All right, so we're going to go into our global configuration mode, and we're going to say track, and we can create, again, a tracking object based on a number. I usually try to make it match. And then I'm going to track, there's several different enhanced object tracking options you can do. if you want to just track an interface, like the line status of an interface, up-down status. If you want to track a list of objects, so if I said list, I can specify Boolean operations. So I can say, okay, if this, right? Now I can create my Boolean operations and say, okay, if this condition and this condition and this condition match, then we're going to go ahead and make the tracking object positive. If one of these conditions doesn't match, we'll make the tracking positive negative. All right. So there's all kinds of crazy things you can do with tracking as well, but we're just going to do a basic track for IP SLA 1, and that's it. All right. Now we can set things like delay and am I going to give it additional thresholds to say, okay, if the IP SLA probe is down, am I going to wait for a specific amount of time that IP SLA probe is down before I bring down the tracking object? Does that make sense? Usually we're just trying to track right against the status of the IP SLA probe. So if I do a show track, we can see that the latest operation code is okay because the IP SLA state is up, and we've applied this tracking object to a route map. I'm not sure what the 0 represents. It doesn't, maybe it indicates one route map, I'm not sure. All right. So now if I go do my trace route, we can see that we're using the serial link as opposed to going over the Ethernet link because the tracking object is up. All right. So let me add some more notes here. So we went into global configuration mode. Track 1, IP SLA 1. And you had some options that you can set there and verify the state of the tracking object with show track. Really, really simple concept, actually. We're relying on an up-down state, operational return code. We can see the latest round trip time, which basically is measured through the ICMP echo request and reply process. But it's a really, really simple concept. If I go to BR1 and I do a show route map, I can see that here we're referencing track 1. The object is up. These are the number of packets that are matching the policy, and so forth. So there's all kinds of interesting things that you could do for the process. We could track, for example, the line protocol of an interface. We can apply this to priority values that we might assign to, say, for example, HSRP or VRRP to decrement priority values so that we can trigger an upstream event, an upstream link event might cause a VRRP or GLBP to trigger, and we'll do a failover or switch over. All right. So we can do a couple of debugs here. Let me show you a couple of the debugs that we can run as well. We can also run debug track all. You can do some specific debugs, but debug track all is usually one that's pretty easy to use. We can also debug IP policy if we want to debug an IP policy. Let's go ahead and generate some traffic. Let me start these debugs. Debug track all. This debug track. Okay, in this case, just debug track. I'm usually used to using the debug track all. And let's do a debug IP policy. All right. Now let me shut down the interface again and see if we see any kind of events triggered here on BR1 based on the tracking object going down. Show route map. So we still see the status is showing up, but we're waiting for the specific threshold. Should have gone down. 20 is 1040, yep. There we go. So it took a little bit of time. You can see this is not very fast, right? So we see here tracking state IP SLA went from up to down. In our route map, we can see that the status is down. So track 1 went to down. That's the other state. If we do our trace route from here, we can see that we're now using the WAN link, the Ethernet WAN link. We can also see based on our policy, all right, we did match a policy in BR1, but the policy was rejected because of the state of the tracking object. So we're going to do normal route forwarding in this particular case as opposed to policy route forwarding. If I bring the interface back up, it'll take a little bit of time here. Oops, go back to BR1. All right, so it still shows down, still shows, all right, now it went it to up. Now if I do the same ping or trace route, we can see that the policy was matched and the packet is now policy routed. These are the kind of debugs that you would be running in the lab to verify your policy operations or even to just troubleshoot policy operations if you have to troubleshoot them as part of the process. Okay? Convergence is definitely not immediate. It's really going to depend on the application profile that you have configured, but convergence is not going to be immediate. If you need something to respond quickly, usually you're going to probably try to rely on dynamic routing protocols or maybe even bidirectional forwarding detection. We'll talk about those concepts a little bit later on. All right. Maybe, the use case here is like if you have a primary ISP and a secondary ISP, but you don't want to run complex BGP configurations and whatnot, you can use, if somebody's internet doesn't work for 5 seconds, it's usually not going to be a critical thing, right? So we can see the logs indicating the up-down state and the down-up state. All right. Let's say we remove, let's try a different direction here. So this is how we've applied policy-based routing to IP SLA and tracking objects to a policy-based routing policy. What if I wanted to do something for default routing as an example? So let's do a show route map. And let's do config T. Let's just take the policy interface Ethernet 1.1, no IP policy, no IP, route map PBR. All right, so I've removed the policy. I should be going over the WAN link, and it shouldn't trigger any debugs here because I'm no longer doing policy-based routing. So we're going over the WAN link. No debugs because we're no longer doing any kind of policy-based routing. Now let's set up a static route, a default route on BR1. And in this case, I want to point the default route over to BR2 unless the tracking object fails. I want to go ahead and use the WAN link as my backup. All right. So what we would do is we would come in here. We already got the probe configured. We've already got the tracking object configured. So all I have to do is add the route, IP route 0.0.0.0, 0.0.0.0, 10.10.30.2. I believe that's correct. Yep, that's the 30 subnet. All right. Track 1. So we've tied the static route to the tracking object. As long as the tracking object is up, the static route is going to be valid. I can also create a secondary route, 0.0.0.0, because we need to be able to define what's going to happen if that default route is not active. And in this case, we'll say 10.10.10. What is the pipe include 10? Oh my gosh, come on. Pipe include 10. So 10, 10, 10, 1. All right. If I do a show IP, well, let me do a show run pipe, include route, SLA, and let me do a section actually, and track. So here's kind of our whole configuration. Here's the IP SLA, and these are, get used to using these kind of grep commands because they're going to save you a lot of time on the exam, no doubt about it. Multiple greps in one to see a bunch of the configuration. So you get a little bit of extra stuff in here because of the route option, but we've got track, there's our tracking object. Here's our static routes that reference, the one references the tracking object. Here's our probe, here's our schedule, and this is irrelevant to this configuration, but because it does reference route and track, it was included in the grep as well. So we can see our configuration. I've got the IP SLA, so do show track. We can see the tracking object is okay. It's now tied to static routing and a route map. So the 0 must, not sure what that 0 means. It's kind of bugging me actually, but it can't be that important. All right. So we've got this tied to static routing. We've got this tied to a route map. Let's go ahead and do a show IP route. And we can see, that's interesting. Oh, I know why. I forgot to do something on the static route. This route is valid because the tracking object is up, but I don't want to load share across the both links with the routing. So what I need to do is I need to put in a floating static route. And I'm going to change the administrative distance of this static route to 2. That last number there indicates the administrative distance of the route. So that's what I definitely want to do. I want to change the administrative distance. Now if I do a show IP route, I should see only one default route. All right, and sure enough, the default route is going to 30.2. Okay. If I do a show IP Ceph, we can also see that 30.2 serial 2.1. So that's the only default route that's actually inserted into the routing table. And naturally, if I do my trace route, no problem. EIGRP, well, that shouldn't, yeah. So now we're doing kind of a longest match. We're doing kind of a longest match here because I pinged the 100 and that has a /24 prefix. This default route's not being matched against that. But that's not really the main concern here. We're talking about a default route. In fact, let me go ahead and just demonstrate this. Do a debug IP packet. Actually, let's not do that. Let's do a debug IP ICMP. Because the debug IP packet's going to be too chatty for us. All right, do a show debug. I might still be getting something from the buffers. Oh, undebug all. Do undebug all. Debug IP ICMP. I'll get there eventually, guys. Sorry about that. Show debug. All right. So I'm debugging my ICMP packets, and what's going to happen here is as I generate traffic, let me ping something that doesn't exist in the topology so that it will go out the default route. And we can see from BR2, that we're definitely getting those ICMP messages. All right, now what happens if that serial link goes down? Config T interface serial 20. Make sure I'm doing the right interface again. Yep, 20. We'll go ahead and shut that interface down. And What should happen now is the default route in BR1 should change because the tracking object went down. Now remember, it does take a little bit of time, but we should see that 30.2 default route go down, and we should see the 10.10.10 route come in. We do a show track. See, the tracking object is still showing okay. So as soon as that tracking object fails, there we go, timeout. Now if I do a show IP route, we've injected this default route instead. So there's all kinds of great things that you can do with IP SLA and object tracking from the perspective of being able to control things. You could apply tracking instances to assigning administrative distances to endpoints, to different routing protocols and so on. All right. So do you guys have any questions about what we've covered to this point? We're just about wrapped up with this topic, but I'm curious if you guys have any questions about the configurations that I did, or if you have any other questions. All right. Trying to think if there's anything else I want to mention about this. I don't think so. I think we pretty much covered everything. I mean, we could look at other SLA configurations, like, what does a UDP IP SLA probe look like, and so on. Let me give you kind of an example of what that might look like. If I'm doing some sort of UDP jitter operation. Again, this would require most likely some sort of response, IP SLA responder, where you'd have to actually set up the responder. That responder config might look like something like this. And I'm just going to try and do this off the top of my head, so I may get some of the syntax slightly wrong. But let's say we're setting up a UDP probe. So the responder config would look something like this. Config T, IP SLA responder. And then we would do IP SLA responder, and we would set up our UDP, I believe it's echo, IP address, and then we would put in the actual IP, and then we might specify the port and the UDP port number. Again, the syntax might not be correct here, and it will depend on the platform as well, but you definitely need to configure a responder. All right. As far as the actual command, it just depends on, what your topology looks like and so on. So on the source device, I would basically do the same thing. But in the case of the source device, where'd my mouse go? There it is. IP SLA source device. It might look something like this: config T, of course, and IP SLA 1, of course. Then we would do a UDP jitter, if that's what we're trying to measure in this case. We could put the destination IP. That's where we're sending the traffic to. The destination port, we don't actually specify in this case the keyword port. And if I wanted to, I could source the traffic like we did with the ICMP echo. And I could say source IP. And I could say source port. So in this case, we would actually have to specify the keyword source port, and then the port number. And there's some other options you could put in there, I suppose. You could identify the number of packets. I've done that before, where you would say number of packets, and you would specify whatever that number is. I guess I could have configured this for you guys, but oh well. Something you can kind of play around with later if you want. And I can also specify the interval of packets, some number value, okay? Just like any other probe, we're going to go ahead and specify our frequency. We're going to go ahead and specify our thresholds and whatnot if we want to. And then we have to schedule the probe just like we did before. All right. The frequency would be in seconds as well. That's an optional configuration because there is a default frequency that gets used. And then we would end up scheduling the probe and so on. There's a bunch of other stuff you can configure as far as the actual, configuration. You could do something like, for example, in this particular case, you could set the history. If you wanted to set the history, allows you to identify how many packet buckets you're going to keep. Statistically wise, you can specify things like how many hours you're going to keep information for. So I might say, for example, history, hours of statistics kept, and then I could put in the time and so on. This is really a whole bunch of different things that you can do. So you can apply net flow labels and so on. My suggestion would be, if you're going to look at some kind of more advanced probes, there's lots and lots of different configuration examples out there that'll work. Okay, so we'll wrap up this lesson here right on an hour and a half. That's pretty good. You guys have any questions that we might want to capture as part of this video before we wrap it up? Any recommendations on additional reference? Ken had a question. What probes are we most likely to see in the lab? The probes that you're going to see in the lab are going to be probes related to specifically one-way probes, where you're not going to have to set up a responder. So it's going to probably most likely be an ICMP echo. I remember I had to create a policy, and that's essentially what they want you to be able to do, set up some sort of policy-based routing based on a probe using some echo request function. Pretty simple stuff, okay? As far as documentation, I'll see what I can throw into the folder in Google Drive for any documents that might be relevant. My suggestion would maybe just to go out and just do a Google search on IP SLA configuration examples. You have the foundation knowledge, so you can go back and look at different examples. And of course, this is a mentorship program. This is not a everything you need to know to take the lab is what I'm teaching you program, right? So you guys should be taking the time to go out and pull up these topologies, play around with the settings, play around with the different thresholds. If you have a question, you can certainly ask me or send a Slack message to anybody in the group, or research it, right? Because this is not an easy process, right? It's not like a little written exam where that's all you have to do. You guys have to know this like the back of your hand. So anyway, let's wrap up this lesson, and we're going to go ahead and get into our next lesson.